Welcome to Breadboarding. In the previous video we got our LED flasher circuit working and we also tried out some flashing LEDs, so we didn't need any other electronic components other than the resistors there. And in this video what we're going to do is to tidy up some of the wires. So all the components here have got pretty long leads and we're just going to tidy up the circuit design here. And we're also going to try swapping out the 555 chip here with this discrete logic transistor 555 circuit. So we'll have a look at that in a few minutes. This is video number 5 in the How to Use Breadboards and Retro Digital Electronics, and in this video we're going to be tidying up our 555 LED flasher, and we'll also be looking at swapping out the discrete logic version of the 555 chip with a little PCB that we've got. So in order to tidy the circuit up, let's just turn it off. We're going to replace this lead here between pins 2 and 6. So this is a jumper cable and it's fine for initially sort of prototyping a circuit, but really what we want to do is to replace it with a decent wire. So what I'm going to do for this is use one of these wire strippers. It's set at about 0.25 of an inch. And what we're going to do is just to bend this so that it actually goes from pin 2 up here round to pin 6 round here. So generally I find that when you're bending these things over, it's normally a good idea just to leave a little bit of insulation after the kink there. And then when you're trying to lay these things out, each person finds their own way of doing it. But basically what I'm going to be doing is just bending it about there. And then we will bend it again out there. Then what we need to do is to cut this to the desired length. So you can see that going to this pin here, so we need to include about another 2.5 holes after that. That's 1, 2.5. And we're going to cut it at an angle. And the reason why I cut the leads like this at a 45-degree angle, it means that when you try and plug them into the holes, then hopefully the cable will go in a bit easier than if you just had a flat sort of bottom to the cable. So then we need to just strip the last bit of this, bend this over, put it in, hopefully be a bit cleaner than the other one. So getting the kinks in these things right is not a precise science, but anyway, that's a bit neater. Now as far as the resistor is concerned, if we just zoom down, it might be a bit easier to see. As far as these resistors are concerned, then we don't really need to change them any way other than probably just trimming the leads a bit. So when trimming them, what I'll tend to do is to trim them at 45 degrees, leaving probably about 1/4 of an inch there, 6mm or so. And then we'll fit them back in again. And it's quite often easier to use pliers for putting these in. That one's in, so I'll just now do the other one. It's a good idea to clear away the spare bits of wire, because if the wire gets onto your breadboard and can short contacts if you're not careful, then this just goes between that one and that one. Okay, this one was already sorted. Now when we come to do the LED, we've got to be a bit careful in that obviously the long lead we know is the anode and the shorter lead is the cathode. So when we're chopping them off, it's probably a good idea to keep that relative length. So we'll still keep the anode slightly longer. So we've still got the anode slightly longer there. Put this in here. And then we've got the LED resistor, our 330 ohm resistor. We'll just chop that leads off there as well. I'll use the grippy pliers. So these grippy pliers, now in fact, now that we've taken a lot of the lead off there, then in fact we can probably move that LED a couple of holes up. We can move that up a hole, move that up a hole. And the flashing LEDs I'm just going to take out for now. We don't need to worry about those for the moment. So we tidied up our thing a little bit. If I was being pedantic about this, I probably would take this out and trim it a little bit more, but for the purpose of this, that is sufficient, and we'll just clear away the dead bits of stuff. Now, one thing I did notice when I was looking at this, I made a lot of effort to make this sort of a chip label, and I managed to get the trigger and the output wrong way round. When I was looking at it, I realised I'd made a mistake there. So when you make a mistake on a chip label, that's the only problem. It can give you very difficult to track down problems. Fortunately, I noticed this quite early. Let's just turn the power on, see if this still works. It's working, good. And what I'm going to do now is I'm going to hook up the oscilloscope first of all, just so we can see some traces on here. So what I'm going to do with the oscilloscope is plug in the leads. So if we just zoom out first of all. So these are oscilloscope leads. When you get an oscilloscope, you tend to need to calibrate the leads a little bit. There tends to be a sort of little screw somewhere that you need to turn to calibrate these. So make sure you read the instructions for your oscilloscope. So you just need to plug the ground or 0 volts in down the bottom there. And this one we're going to plug into the capacitor value. And just, it's turned off, yes. Plug this one into the output, which is going to the LED. We're just going to look at the oscilloscope trace here. So you can see both of them are at 0 at the moment. And when we turn this on, what we're going to see hopefully is the waveforms of the across the capacitor and the output to the LED. And what I'll do is I'll stop the oscilloscope running once we've got the initial ramp up and a couple of cycles. So we're just going to start that now. Okay, so hopefully just move it across here. So what you can see here is you turn the power on, you can see that the first cycle that the capacitor charges up to, I think this was about 3.3 volts. Then it discharges down to about 1.67 volts, and then it goes on this cycle all again. The first flash is a little bit longer, but then after that we're talking about 3 flashes a second or so. And you can see there's a little bit of a spike here. So in fact, when the LED, when the output first turns on, there must be a short period of time before the LED really fires up, where we get up to about 5 volts there, and then it drops back down once the LED is illuminated. But that's what we would expect. What I'm going to do now is to swap out the transistor 555 circuit and see whether or not we get the same thing. So before we swap out the chip for the discrete version of the 555 timer, let's just have a little look about it. So this one again is one I've got from Bitsbox. So if we just click on here, you can see it's not cheap. It's about £8.10 versus the 555 is it's a lot less than that. And you can see the image of the thing there, and there's also a schematic diagram. So I've taken those and we're going to be using those as we go through stuff. So you can see here that it's got 8 pins just like the original chip, but then you can also put pins in the bigger bits here if you want to also use those, but we're just going to be replacing the current chip. And what we should be able to do is to find the certain points on the circuit to be able to find certain test points which perhaps we can't see with the normal IC integrated circuit. So there should be a couple of points on the chip here where we can look at the inputs to the flip-flop, for example, for the set and reset signals. So this is the schematic for it, and you can see it's basically got 2 types of transistors. There's a 3904 and there's a 3906. Now, the 3906 is a PNP transistor. This means when we see the symbol that the arrow is pointing inwards towards the base here. And you can see then that because it's a surface mount device, then in fact the collector, base and emitter appear in that sort of form. And then the 3904 is an NPN transistor, so that means that the arrow is facing outwards towards the emitter. And majority of the time it's easier to think about NPNs in that we put a voltage on here and it lets a larger current go through the collector to the emitter. PMP, probably not quite as easy to get your mind around, but for the moment, all we're going to be doing really is looking at this and trying to work out whereabouts we need to put the test probes to see some of the other signals. And in fact, what you can see here on the diagram, you can see there's 1, 2, 3, 1, 2, 3, and what I've done, I've annotated the diagrams here with the 1, 2, 3, 1, 2, 3. We can see here on the chips where the appropriate pins will be. So this is the diagram that we had in some of the earlier videos that explained what the 555 timer chip has inside it. So the set reset latch has a reset input and a set input. Now, we can't normally get access to these because they're not available in the external pins. And what we were just looking at earlier, we had the oscilloscope probe on the trigger threshold input, which was also connected to this capacitor. And we also had the other output connected to the output here as well. So the oscilloscope values that we've seen, we've been able to see this capacitor voltage, including the ramp up from 0 volts. And we've also seen the output here. What I'm going to try and do now is see if we can actually find the input to this SR latch here coming out of the two comparators. So this is a schematic, and these are the two signals we've been looking at already. Now what we want to do is, in fact, the PMP transistor here, you'll see that the way how it's actually located up here is, in fact, the emitter is at the top. So what I've done here is I've just done this round so that we can actually line these up and can use this to work out where we actually need to find the signals. And in fact, I believe the set and reset are actually these parts of the schematic. And by looking at the discrete 555 under the microscope, I think I've managed to work out whereabouts these will be. The easiest way seems to be to look at where we've got certain value resistors, because the 100K only exists in a couple of places, and the 4.7K as well is in a couple of places. So by looking at where these are, should hopefully be able to work out whereabouts we need to put the oscilloscope probes. And from looking at it, this is the area of the circuit board, I think, where we may need to try the oscilloscope probes to see if we can see the inputs to the set and the reset. And we'd expect that with these comparators here that we would have the set signal will be 1 until such time as we get above 1.67 volts on the capacitor here. This will be 0, and then when it gets above 3.3 volts, we'd expect to see this to go positive, and then it will go back to 0 again as things discharge. So we should see a blip on each of these somewhere around the beginning and the end of the discharge of the capacitor here. So I'm going to leave the capacitor plugged in, and we'll take this output here and we'll actually try and connect it to these two things here. Let's just stop the circuit. Just remove this out of the way for the moment. So this is a chip puller, an IC removal tool. There's various forms of these, but it's a lot easier to actually get the chip out without damaging it in this way. And then we're just going to put our 555 discrete transistor in there. Make sure we line it up properly. And we'll just switch that on and just plug our oscilloscope lead back in again. Switch it back on, see if it's working. Yep, that's working. We'll just check the oscilloscope again. Okay, so that looks pretty much the same as what we had before. So that's looking good. So now what I need to do is to try and find those points, and we'll see whether or not we can actually see the inputs to the SR latch and see if we can see the two signals coming out of the comparator. So I'm just going to try and do the reset first, and then we'll do the set. So we'll switch this over to the oscilloscope. You can see at the moment we've just got the capacitor charging and discharging. If we zoom in, so the first point we want to look at is just on the end of that resistor. And if we switch back You can see that certainly seems to be an output there. So this is the reset output that will cause the discharge of the capacitor. So that looks to be correct. And now we'll switch it over to the set. And you can see that when the set is set, then we see that the capacitor is actually charging. So it looks like we've managed to find two of the points where this is. Now the voltage here is not a normal logic level. It's not sort of like 3.5 volts that we'd normally have for a logic 1. Because this is a discrete logic circuit, it only needs to be about 0.7 volts to turn on the transistors here. But we'll be looking at the next video what sort of voltage levels we need to turn logic gates on and off. So this is only a short video. We've finished tidying up the 555 LED flasher, and we've also tried out our discrete logic 555 board. Now in the next video what we're going to be looking at is starting to look at logic gates and the chip families. So we'll be looking at transistor logic, TTL, and this is the logic types that we tend to use for retro microprocessors. So certainly things like Z80s, 6502s, 8080s, 8088s, 6800s, 6809, 68000, all these sort of microprocessors that all use logic gates and TTL compatible chips. So thanks for watching. If you don't want to miss out on future videos, then please hit subscribe. And if you can hit like as well, it just helps to make the videos available to more people. Thanks for watching.